Dear student, warm welcome to NPTEL Phase 2 program video course on Geosynthetics Engineering in Theory and Practice. My name is Professor J. N. Mandal, Department of Civil Engineering, Indian Institute of Technology, Bombay, Mumbai, India. Lecture number 56, Module 12, Design of Geosynthetics for Landfill. I will now focus the recap of the previous lecture, seismic analysis in venice slope stability, uniform thickness cover soil with reinforcement, runout and anchor trench design after Cohen et al. 2002 and Cohen at 2005, application of geosynthetic clay liners or geomembrane as a liquid containment liner after Cohen 2005. Now, I will address the geosynthetic clay liner GCL as a composite liner after Cohen 2005. When the geosynthetic clay liner are used with the geomembrane in landfill liner, leachate flow is affected due to the presence of the geosynthetic clay liner. So, what it will happen, sometimes it has been observed that if there is no geomembrane or the geosynthetic clay liner, then leachate can percolate through the ground surface and polluted the ground, and also this leachate flow that's vertically downwards at any depth and pose a great pollution problem. So, here we are providing a kind of the geosynthetic clay liner which is made of the bentonite and the geotextile at the top and the bottom, and a geomembrane in which the leachate can pass through this geomembrane. Suppose if there is any hole into the geomembrane, then and below that geosynthetic clay liner, you can see here that leachate propagated almost in the horizontal direction rather than going down vertical direction. So, this is one of the major advantage for the use of the geosynthetic clay liner or the geomembrane as a liner. So, that is why this geosynthetic clay liner as a composite liner. So, it is more useful and it will not be polluted the ground surface, because the leachate flow direction is absolutely the different from as usual in the traditional method. The flow rate or the leakage rate is calculated from the formula given by the Giroud and Bonaparte 1989. Q is equal to pi Ks HW plus T into D divided by 1 minus 0.5 D by T, or Q is equal to pi into Ks HW plus T divided by A ln 2T divided by B, where Q is equal to flow rate, Ks is geosynthetic clay liner permeability, HW is the total head loss, and T is equal to geosynthetic clay liner thickness, and B is the length of silt in the geomembrane, and D is the hole diameter. So, I am giving the design example. The following properties of the geosynthetic clay liner and the geomembrane have been used in the landfill slope stability model or LSS model to determine the leakage rate through the composite liner. Here geosynthetic clay liner permeability is 7 into 10 to the power minus 12 meter per second, total head loss is equal to 300 millimeter, and geosynthetic clay liner thickness is equal to 10 millimeter, length of the silt in the geomembrane is equal to 2 millimeter, and hole diameter in the geomembrane is equal to 2 millimeter. Now, this we have put this input data formulation in our LSS model, and this problem statement that this software calculate the what will be the leachate from any sealed or hold in the geomembrane and overlying by geosynthetic clay liner. Here input data is permeability of the geosynthetic clay liner is equal to 7 into this data we have put 7 into 10 to the power minus 12 meter per second, and thickness of GCL is equal to 0.010, that is in meter, and total head for the composite liner is equal to HW is equal to 0.300 meter, and length of the geomembrane that is equal to about 0.002. Now, or you can have the whole diameter of the geomembrane, that is small d is equal to 0.002 meter. So, if you put this input data into this LSS program and then you can calculate, so you can obtain the output of this result, that is leakage rate per unit length of silt in the geomembrane, that is Q is equal to 2.96 meter cube per meter second, or the leakage from the hole in the geomembrane, that is Q is equal to 0.015 into 10 to the power minus 12 meter cube per second. So, there is the possibility for the leakage may occur due to the length of the silt, or this may occur if there is any hole. I have also shown you that how you can detect the leakage of any geomembrane when the geomembrane is placed below the water. So, I have mentioned that how you can detect the hole. So, here in this problem we observe that what should be the leakage unit length of silt in the geomembrane, or leakage flow if it is a silt or if it is there is a hole. Now, this result at compared with the LSS model with the Cohenor 2005 model case, when the leakage from the silt, the Cohenor 2005 given 2.96 into 10 to the power minus 12 meter cube per meter sec, and from the landfill slope stability model this value is 2.96 into 10 to the power minus 12 meter cube per second. Leakage from the circular hole, that is Cohenor is given 0.015 into 10 to the power minus 12 meter cube per second, and LSS model gives 0.015 into 10 to the power minus 12 meter cube per second. So, it is matching 100% in both the cases, either the leakage from the slit or leakage from the circular hole. So, this model is very appropriate for the determination of the leakage. Now, I will show our landfill slope stability model. When you will design the landfill, then you require the proper kind of the design. So, when you will design this landfill, then you must go to all this point. So, you must go near about maybe 29 point. This is the landfill slope stability model, and this is developed by J.K. Soni, and this software package deal with the following geomembrane or geosynthetic clay liner related material. So, we are to go through all these cases. So, it may be beneath slope stability analysis without reinforcement. This is by Cohenor and Sung 1998, and I will just show you one by one. And already I have also shown you that how you can calculate the factor of safety against the beneath slope stability analysis. Here I wanted to focus in this model how you can use this software. So this is the problem statement to determine the factor of safety for the geosynthetic clay liner or geomembrane line slope when the reinforced uniform thick cover soil is used. So this is the input data, that is for the slope characteristic. That means you should know what will be the length of the slope, you should know what will be the height of the thickness, you should know the slope angle. And also you should know cover soil property, which is unit weight of the cover soil, also friction angle of the cover soil, pi, and the cohesion of the cover soil. That is gamma is 17.5, pi is equal to 30 degree. And apart from that, you require the GCL or geomembrane property, that is what is the adhesive between geosynthetic clay liner and the cover soil Ca is equal to 0, or interface friction angle between the geosynthetic clay liner geomembrane cover soil, that is in 15 degree. So you have to substitute in this model, these are the input data, and then you can calculate and can determine that what should be the weight of the active weight, that is in 178.496 kilonewton, weight of passive weight WP 2.60 kilonewton. Also that interweight force acting on the active wedge from the passive wedge EA is 2.459, and interweight for active wedge on the passive wedge from the active wedge is EP is 2.459, and you find here that factor of safety value is equal to 0.842. So we have already solved this problem. I have shown you that earlier in my course presentation, but here I am just showing how to make use of this software. So now, because this factor of safety is less than 1, then you have to adopt some tree system. So you can provide the tapered cover soil instead of uniform thick cover soil. A. B. You have to providing the geotextile or the geogrid reinforcement along the side slope. And C. By alternating the slope geometric configuration, either by decreasing the slope angle or by increasing the cover soil thickness, then you can make the slope stable. Let us say that in case of A, if we provide the tapered cover soil instead of the uniform thickness. So if you go for tapered cover soil, that means this will be like this tapered cover soil. Initially it was a uniform. Okay? So now this is the tapered cover soil has been used. So if you provide with the tapered soil, then and if you substitute the value of the slope angle and that what will be the length, what will be the thickness of the cover soil, and what will be the thickness of the cover soil at the bottom measured vertically, that is capital D is equal to 0.30 meter, and slope at the top of the cover soil is 16 degree, and cover soil property, that is unit weight of the cover soil is 17.5 kilonewton per meter cube, friction angle of cover soil is pi 30 degree, and cohesion of the cover soil is C is 0. And geosynthetic clay liner or geomembrane property, that is adhesion between the geosynthetic clay liner geomembrane and the cover soil, that is Ci is equal to 0. Interface friction angle between the geosynthetic clay liner and geomembrane and cover soil is about delta is equal to 22 degree. So if you substitute or input this data, okay, case A, so this is the output, weight of the active wedge WA is equal to 508.706 kilonewton, weight of the passive wedge WP is equal to 82.488 kilonewton, and interwedge force acting on the active wedge from the passive wedge, that is EA is equal to 36.503 kilonewton, interwedge force acting on the passive wedge from the active wedge, that is E of P is equal to 36.503, and you see here that factor of safety value is 1.543. Since if the factor of safety value is greater than 1, that is the force tending to slide the covered soil over the geomembrane in geosynthetic clay liner are less than the resisting forces, so design is stable and the safe. Now if I go for this second case, here I am also that showing that initially this is the uniform, it was there in the beginning. So now if I go for the B, where you want to introduce the layer of the reinforcement material. So if you want to introduce the layer of reinforcement material, this here the red color, which will give you the layer of the reinforcement along the slope. Okay, we are adding the second case, that is B case, that where we are using this reinforcement. Now we are substituting this value input data, the soil characteristics, that is the length of the slope, the L is equal to 35 meter, and the thickness of the covered soil is 0.3 meter, and slope angle beta is 18.4 degree, and covered soil property unit weight of the covered soil gamma 17.5, and angle of friction of the covered soil pi is equal to 30 degree, cohesion value is equal to 0, and geosynthetics clay and geomembrane property Ca is 0, delta is about 15 degree. Now here we are adding this reinforcement, either the ultimate tensile strength of the reinforcement geotextile or geogrid is 300 kilonewton, and we are considering that reduction factor for the installation damage RFID is 1.25, reduction factor for the creep, that is RFCR, is equal to 1.28, and reduction factor for chemical and biological degradation RCBD is equal to 2.0. So reduction factor for the seam, because it is requires some joining the geotextile or the geogrid material, so RFSM is 1.25. So for the introduction of the reinforcement for slope stability, now we calculate and we find that output, that is weight of the active wedge WA is equal to 178.496 kilonewton, weight of the passive wedge WP is equal to 2.63 kilonewton, interwedge force acting on the active wedge from the passive wedge EA is 1.216 kilonewton, interwedge force acting on the passive wedge from the active wedge, that is EP is 1.216 kilonewton, and the factor of safety value is Fs is equal to 1.507. So comments, since this factor of safety value is greater than 1, the force tending slide the covered soil over the geomembrane and geosynthetic clay liner are less than the resisting force, so the design is stable and safe. So design also is for the static condition only, but if you want to include the seismic analysis in this design, yes, you can. So if you add the seismic analysis, seismic also into this, then so if you want to, you are calculating this. Now if you wanted to include the seismic also, yes, then this problem statement, the seismic analysis for beneath slope stability, that problem statement, the slope stability program utilize the pseudostatic analysis to determine the factor of safety Fs of a geosynthetic clay liner slope when the reinforcement uniform thick covered soil is used. Here input data, the soil characteristics, that is length of the slope L is equal to 35 meter, then slope angle beta is equal to 15 degree, and thickness of the covered soil H is equal to 0.35 meter, and cover soil property, that is gamma is 18 degree and C is equal to 0, pi is equal to 32 degree, and geosynthetic clay and geomembrane property, that is delta is equal to 18 degree and Ci is equal to 0. Apart from that, you have to add that seismic characteristic here. So, average seismic coefficient we have include Cs is equal to 0.30 and reinforcement detail. So, reinforcement detail, ultimate tensile strength of the reinforcement geotextile or geogrid, T ultimate equal to 100 kilonewton. So, reduction factor for the installation damage 1.25, reduction factor for the creep 1.28, reduction factor for chemical and biological degradation, that is 2.0, and reduction factor for the SIM 1.26. So, if you consider even then seismic force, and then you can also calculate it what should be the factor of safety. So, here output weight of the active waste WA is equal to 211.681 kilonewton, weight of passive waste WP is equal to 4.412, and the interface waste acting on the active waste from the passive waste, that is EA is equal to 1.921, then interwaste force acting on the passive waste from the active waste, that is EP is equal to 1.921. So, factor of safety 1.335. So, comment, since the factor of safety value in the seismic condition more than the 75% of factor of safety value in static condition. So, the design is safe and the stable. So, we consider the seismic forces and also find that how you can calculate this factor of safety due to the seismic force. Now, in the SEEK, that by altering the slope geometry and the configuration, either by decreasing or slope angle or by increasing the slope angle, that also you can change this. So, we are keeping almost this slope characteristics value, that is the length of the slope, the height of the thickness of the cover soil, this friction angle, also this is the soil cover property, that is gamma, pi and C, and that is gamma is 17.5, pi is 30 degree, C is 0, and the geotextile geomembrane property, that is adhesion value 0, and the interface friction between GCL and geomembrane soil is 35. So, you can calculate and then you can have the output of this, and you find here the factor of safety value is less than 0.642. So, next, that Vinit slope stability analysis with reinforcement. So, this problem statement to determine the factor of safety GCL or geomembrane liner slope when the reinforcement is uniform covered soil. So, this is the slope characteristic. You know what will be the length of the slope is given 35 meter and the thickness of the covered soil 0.3 meter and slope angle beta 38.4, and covered soil property is given, that is gamma is 17.5, pi is 30 degree, and this cohesion value is equal to 0, and geotextile geomembrane property Ci is equal to 0, delta is equal to 15, and here is the reinforcement detail is given with that 100 ultimate tensile strength. These are all the reduction factor, and then you can calculate and you can determine what will be the factor of safety. This factor of safety is come 1.507. So, since this factor of safety is greater than 1, then force tending the slide the covered soil over the geomembrane or geosynthetic clay liner are lesser than the resisting force. So, design is stable and safe. Now, design is static condition only, but you can also calculate it for the seismic condition also. So, if you want to calculate the seismic condition also, you have to add the average seismic coefficient value CS is equal to 0.10, other remain as it is. So, you can calculate and you can obtain this value 1.335, and you find that this value is about 75% of the static value, then it is okay. Now, Vinny slope stability analysis of Temperate covered soil. This is like Koiner and the Sung 2005. Here, when the taper covered soil, this you have to provide this, it is like this is designed like this, taper covered soil, like taper covered soil analysis, and you are to input data, slope characteristic. Here slope angle beta is equal to 18.4 degree, length of the slope measure from along the geosynthetic clay liner, L is equal to 35 meter, and the thickness of the covered soil at the crest perpendicular to the surface HC is equal to 0.15 meter, and thickness of the covered soil at the bottom measured vertically, that is D, is equal to 0.30 meter, and the slope at the top of the covered soil, that is this small of W is equal to 16 degree. Now, covered soil property, unit weight of covered soil gamma 17.5 kilonewton per meter cube, friction angle of the covered soil pi is equal to 30 degree, and cohesion of covered soil C is equal to 0. And geosynthetic clay liner and geomembrane property, that is adhesion between geosynthetic clay liner, geomembrane and the covered soil, that is Ca is equal to 0. Interface friction angle between the geosynthetic clay liner or geomembrane and the covered soil, that is delta is equal to 32 degree. Now, this is for the taper covered soil. So, this is the output of the taper covered soil analysis. The output is weight of the active wedge W is equal to 508.706 kilonewton, weight of the passive wedge WP is equal to 82.488, then interwedge force acting on the active wedge from the passive wedge EA 36.503 kilonewton, interwedge force acting on the passive wedge from the active wedge, that is EP is equal to 36.503 kilonewton. So, you will obtain the factor of safety Fs is equal to 1.543. So, here comments, since the factor of safety value is greater than 1, so the force tending to slide the covered soil over the geomembrane or geosynthetic clay liner are less than the resisting force. So, design is the stable and the safe. Now, next is Vinny slope stability analysis for the Temperate covered soil, and here the reinforcement covered soil has been used. Here reinforcement has been used. So, in case of the reinforcement, and this is the figure, you can see here in a taper covered soil analysis with the reinforcement, the red one is the reinforcement. This is D, capital D is this one. Okay. So, then you are to include the what will be the slope characteristic, that is beta is equal to 20 degree, then L, the length of the slope is 35 meter, and thickness of the covered soil HC is 0.15, and thickness of the covered soil at the bottom measure vertically D is equal to 0.30, and slope at the top of the covered soil, that is small w is equal to 16 degree, and covered soil property gamma 17.5 pi is 30 degree and C is equal to 0. Geosynthetic and the geomembrane property Ca is equal to 0, delta is equal to 20 degree. This is the reinforcement in detail is given. Ultimate tensile strength of the reinforcement geotextile T ultimate is 100 kilonewton, and these are the all reduction factor for the installation damage, reduction factor for creep, reduction for chemical and biological degradation, and reduction factor for seam, and then you calculate. You can have the output the weight of the active phase WA is 775.967, for passive WP 207.999, and the EA is 66.88 kilonewton and EP is 66.88 kilonewton and factor of safety 1.64. So, you find that factor of safety value is greater than 1. So, it is the safe and the stable structure. So, now we will discuss seismic analysis for beneath slope stability analysis without reinforcement, that is Queen 2001. So, this is seismic analysis for beneath slope stability analysis. Here the slope characteristic, the length L35, beta 15 degree, H is 0.35 meter, and cover soil property gamma is 18 degrees, C is equal to 0, pi is equal to 32, and GCL geomembrane property delta is equal to 18, CA is equal to 0, and here the seismic characteristic, the average seismic coefficient CA is 0.10. So, you can calculate. So, you will obtain the factor of safety value. Here two cases, one that factor of safety is 0.905, but factor of safety in static condition is 1.273. So, comment, since the factor of safety value in seismic condition is less than 75% of factor of safety of static condition, so the design is not safe in the case of sliding over the geosynthetic clay liner or the geomembrane is anticipated. So, you can use the following approach to make this design stable. A, by providing the geotextile or geogrid reinforcement at the side slope, and by altering the slope geometry or configuration either by decreasing the slope angle or increasing the cover soil. So, if you can add the reinforcement here, the seismic analysis for beneath core soil with the reinforcement. So, this red color is shown that reinforcement, and here due to the seismic, that is CS into WP in the passive waves, that is seismic coefficient CS, and here is the seismic coefficient CS, this is in the active zone, this is CS into WA. So, now if you consider this seismic effect for the beneath slope stability analysis, and then you can calculate and you can determine that what will be the factor of safety. This is coming 1.335. So, it is stable because it is greater than the 1. Now, seepage force analysis, beneath slope stability, this Koiner and Sung 1996. So, if there is a seepage. So, seepage force analysis for beneath slope stability, seepage can build up in the cover soil in two different ways. One, horizontal build up seepage like this from the toe and upward, this is the case, and two, the parallel to the slope, this one, this is parallel to the slope seepage build up outward, this is case of B. This is the geomembrane or geosynthetic clay liner, and we will show that how can we determine if the horizontal seepage build up. You also can determine the seepage forces analysis by beneath slope stability when the parallel slope. So, if it is a horizontal build up, you go, and this is the problem statement, the slope stability program, determination of factor of safety for geosynthetic clay or geomembrane line slope when the seepage is built horizontally for uniform thick cover soil. Here you to put the input data, that is slope characteristics, that is the vertical height of the slope is capital H is equal to 15 meter, and the slope angle beta is 20 degree, and the thickness of the covered soil H is equal to 0.60 meter, cover soil property, that is unit weight of the cover soil 17.3 kilonewton per meter cube, cohesion value is equal to 0 and pi value is equal to 35 degree, and also that is the saturated unit weight of the cover soil, because we are considering the seepage. So, this gamma saturated is 18 kilonewton per meter cube. Geosynthetic clay or geomembrane property, that is delta is equal to 22, and the seepage characteristic, this is the vertical height of the free water measured from the toe, that is HW is equal to 1.5 meter. So, if you now calculate, so you can obtain the output for the seepage force analysis for unit slope stability, and this is WA is 447.215, WP 10.085, EA is 2.217 kilonewton, EP is 2.217 kilonewton, and factor of safety value 1.089, and the horizontal submergency ratio HSR is equal to 0.1. So, comment, since the factor of safety value is greater than 1, the force tending to slide the covered soil over the geomembrane or geosynthetic clay liner are less than the resisting force. So, design is stable. I will show you the horizontal build-up is the parallel to the slope seepage build-up. So, like this parallel to the slope, if it is happen, then how you can make use of this program. This is the problem statement. The slope stability program determine the factor of safety of geosynthetic clay liner slope when the seepage build up parallel to the slope for uniform thickness. Here input data, that slope characteristics, that is veneer height of the slope h is equal to 15 meter, beta angle 20 degree, and h is equal to thickness of the cover soil is 0.6 meter, and cover soil property, that is gamma 17.5 kilonewton per meter cube, C is equal to 0, pi is equal to 35 degree, gamma saturated 18 kilonewton per meter cube, and geosynthetic and geomembrane property delta is equal to 22 degree, and seepage characteristic, that is seepage water head in the covered soil, that is HW is 0.06. So, you can calculate and can determine what will be the factor of safety. This factor of safety value is 1.108, and parallel to the submersion ratio, which is called PSR, is 0.1. So, here we find the factor of safety value is greater than 1, so it is safe. So, now the run out and the anchor change analysis of sand, Koiner 1997, that is run out or anchor change. I have shown you that in my earlier presentation, that do you want to provide only run out length, or do you want to provide both run out length and the rectangular anchor change, or number 3, do you want to provide both run out length and the V-shaped anchor change. So, this is run out length L R0, you know this is the run out length L R0, and this is the anchorage range, that is DAT rectangular type, or it may be the V-shaped type. Okay. So, suppose you want to go for the run out length, then you go, and then if this is the run out problem statement, the slope stability program determine the run out length when there is no anchor change provided. So, input data, soil characteristics, slope angle beta 18.4 degree, and thickness of the cover soil h is equal to 0.30 meter, and cover soil property unit weight of cover soil gamma, that is 16.5 kilonewton per meter cube, and GCL and geomembrane property, the allowable stress of GCL or geomembrane, that is sigma allowable is equal to 7000, that kilonewton per meter square, thickness of the GCL or geomembrane, that is 1.0 millimeter, and the friction angle of GCL or geomembrane to the soil below the GCL, that is delta L is equal to the 30, and the friction angle of the GCL or geomembrane to the soil above the geocell, that is delta A is equal to 0 degree. Now, you can calculate and you can find that what will be the length of the GCL or that is L is 0, that is 1.888. So, comment if it is a greater economy and stability achieved by providing the anchor trench at the end of the runout length, it will result to reduce the runout length. So, user can go of these two types of the anchor trench, either the rectangular anchor chain or V-shaped anchor trench. So, if you go for the, this is the problem statement, the slope stability program, determination required depth of the rectangular trench anchor for different runout length. Now, if you go for the runout length, then here the input data for slope characteristic beta is 18.4, H is equal to 0.35, cover soil property gamma is equal to 18, pi is equal to 30, and the allowable stress for the geosynthetic clay liner sigma allowable is 3500 kilonewton per meter square. Thickness of the GCL, that is T, is equal to 7 millimeter because this is a GCL, and the friction angle of the GCL to the soil below the GCL, that is delta L is equal to 20 degree, and friction angle of the GCL to the soil above the GCL, that is equal to 0, and then runout length, let us say LR0 is equal to the 1.0. So, then you can obtain the output data, what will be the design of the anchor trench, that is DAT, which we are interested. That means DAT is equal to 0.588, and runout length L20 is equal to 1 meter. So, you can calculate PA and also the PP. So, comment depth of the anchor trench can be increased or decreased by decreasing or increasing the runout length. 2. If the user is using the any geotextile or high density polyethylene geomembrane, then he may face the problem to bend and bury. It is the narrow rectangular anchor trench. So, for this case, that V-shaped anchor trench are recommended. So, do you want to design this problem with the V-shaped anchor trench? If you say yes, then you can. So, you can use, this is the problem statement, the slope stability program, determine the required depth of the rectangular anchor trench for the different. So, here slope characteristic beta is 18.4 and the thickness is 0.3. This is the cover soil property, that gamma is equal to 17.3, pi is equal to 35. This is geosynthetics and geomembrane property, T allowable is equal to 19.8 kilonewton per meter, and the friction angle between GCL and the underlying soil delta C is equal to the 18, and this is the friction angle between GCL and the backfill soil, that is delta is equal to 22 degree, and runout length LR0 is equal to 0.9, and the left bottom angle of the V-shaped anchor trench, that is alpha of L is equal to 60 degree, and this right bottom of the V-shaped anchor trench, that is alpha of R is equal to 30 degree. You can have like this is a V-shape, this is a V-shape like this. Okay. So, for this V-shape you can also calculate, and this is the output, that is depth of the anchor trench. Okay. And you can have DAT is 0.77, LR0 is 0.9 meter. So, depth of the anchor trench can be increased or decreased by decreasing or increasing the runout length. And here A of B, which is runout length, LR0 is equal to 0.90 meter, and BC you can calculate 0.88 meter, and CD this is 1.53 meter, and alpha L is equal to 60 degree, and this alpha R is equal to 30 degree. Runout length an anchor trench analysis for sand. The output depth of the anchor trench, that is DAT, is equal to 0.77 meter, and runout length L at 0 is equal to 0.9 meter. So, in case of V shape, you know that this is the A of B, that is LR0 runout length, that is LR0 is 0.9 meter. You can calculate BC also 0.83 meter. This is the CD is equal to 1.53 meter, and also DAT, this depth, that is 0.77 meter, and also the alpha of L is 60 degree and alpha R is equal to 30 degree. So, depth of the anchor trench can be also increased or decreased, or by decreasing increasing the runout length. So, instead of the rectangular shape, it is sometimes very difficult to make it 90 degree in the geomembrane. So, in that case you can go ahead with the V shape, because you can bend it at 60 degree or the 30 degree, and also it is much more convenient to use this. So, next, waste mass failure analysis, Quench 2003. In the landfill, you can see that after the waste material in dumping and landfill, then you find that there is a failure of the waste mass itself, and also that there is a translation failure of the waste mass. This is the waste mass, how it fell. So, if the waste mass failed, it is also necessary to proper design this. So, in this program also, this problem statement, this program determine the factor of safety value for the landfill for translation waste mass failure analysis. The input data, that is geometric data, that is height of the side slope H is equal to 30 meter, and top width of the slope B is equal to 20 meter, and the slope angle beta is equal to 18.4 degree. Landfill subgrade percentage is 1.1, and waste field slope alpha percentage is 14, and solid waste properties, that is friction angle of the solid waste, that is pi SW is equal to 20 degree, and the unit weight of the solid waste gamma SW is 10.2 kilonewton per meter. Liner property, that is the interface friction angle of the bottom liner system, that delta P is equal to 17, and also the interface friction angle of the slope liner system delta A is equal to the 17 degree. So, now if you calculate this, so you can have the output, that is minimum factor of safety lower bottom solution Fs minimum 1.334, and the maximum factor of safety of the upper bottom solution Fs maximum is 1.454, and average factor of safety, that is Fs average 1.394. So, this is safety and the safe, then it is okay. So, application of the GCL as a liquid containment liner. So, here the geometric consideration and thickness consideration. This is important. I also mentioned this geometric and thickness consideration. This is the input data, what will be the storage volume required. Let us say this is the V and this is in liter, and you know that what will be the width of the ground surface, that 100 meter, length of the ground surface is 100 meter, and the slope ratio, that is horizontal to vertical, S is equal to 4. So, you can calculate and can determine that what will be the required height of the liquid containment system, that is H is equal to 4.16. So, you can calculate the height on the basis of the theoretical analysis. However, the liner impoundment must be somewhat deeper to allow the freeboard against the overfilling, wave action, and so on. And if you go thickness consideration, so thickness consideration, this is the problem statement. The program determine the required thickness of GCL or geomembrane liquid containment system for the landfill. The input data allowable, that geomembrane, that stress, that is sigma allowable is equal to 200,000, that kilonewton per meter square. This is mobilization distance of the geomembrane x is equal to 100 millimeter. Then steep that is the settlement angle mobilized the geomembrane tension in degree, beta is equal to 45, and the angle of shearing resistance between the geomembrane and the upper soil or the geotextile delta U is equal to 0, angle of shearing resistance between geomembrane and the lower soil or the geotextile in degree delta is equal to 30 degree, water reservoir height H is equal to 8 meter, and the unit weight of the filling material, that is waste or the water, that is gamma, is equal to 9.81. Now, if you substitute this I am showing you that what will be the figure like that. This is the x. This I have already also explained how you can calculate the thickness. So now with this program, then ultimately you can have the required thickness of the geomembrane or geosynthetic, that is H is equal to 0.766 millimeter. So sometimes though it is 0.776, it is preferable always you put in the hard thickness, then you can give the 1 meter or you can 1.5 or 2 meter. So because it is sometimes necessary that when you dump this any waste material and is compacted, there is a possibility for the damage of the geomembrane. So it is preferable that you can give a little bit hard thickness. So then contaminate and transport of GCA, then this is a contaminant transport through the geosynthetic clay liner and compacted clay liner. This is steady adverse mass flux. So their problem statement, this program determine that contamination transport to GCL and geosynthetic clay liner through the steady advection. The input data geosynthetic property hydraulic conductivity K of GCL is 0.0000001. Then thickness of the liner is given, LGCL is 0.7 centimeter, and GCL property hydraulic conductivity is given K of GCL is this value, and thickness of the liner, that is LCCL, is equal to 90, and water and leachate head on the top of the liner H is equal to the 30 degree. So you can calculate what will be the advective mass flux ratio, that is RA is equal to 0.33. Since the RA value is less than 1, therefore geosynthetic clay liner is superior to the compacted clay liner in terms of the steady advective mass flux through the liner. And if it is a steady diffusive mass flux, this is the problem statement. The program determines the contamination transport through GCL and the CCL through the steady diffusion. So input data GCL property effective diffusive coefficient, that is D for the geosynthetic clay liner is this centimeter per second. Thickness of the liner, that is LGCL, is equal to 0.7 centimeter, and the porosity, that is for GCL, is 0.6, and the CCL compacted clay liner property effective diffusive coefficient, that is D centimeter per second, is this value, and thickness of the liner, that is LGCL, is equal to 90 centimeter, and porosity, that GCL, is equal to 0.5. So if you substitute this input data, you can have a output data, that is the diffusive mass flux ratio RD is 51.43. Since the RD value is greater than 1, so therefore geosynthetic clay liner is not equivalent to the compacted clay liner in terms of the steady diffusive mass flux through the liner. So now this software also deal with the following landfill designed for the related problem, that cover soil slope stability landfill gas pressure. If there is a development of the gas pressure, so this problem statement, the software also determine the safety factor of the slope stability of the landfill cover subjected to the landfill if gas pressure undermine the geosynthetic clay liner. That is slope characteristic, that is thickness of the slopes of the pipe perpendicular to the slope, that is in H meter is 0.6 meter and beta angle is equal to 16.7 degree, and cover soil property unit weight of soil gamma is equal to 16 and C value is equal to 0, and geosynthetic K-liner property, that is CS is equal to 0, delta is equal to 22 degree, and LHG pressure, that is kilopascal, that is G is equal to 2 kilopascal. So, if there is a development of cover soil or there is a development of gas, if gas develops, there is a leachate and gas pressure developed here. So, you have to calculate that what will be the factor of the safety. So, you can calculate and you find the factor of safety value 1.05, then it is okay. Now, for the lateral drainage system for unit gradient ratio, for lateral drainage system for unit gradient ratio, so this is the geocomposite or geosynthetic clay liner, this is the gradient I, and here that input data is the drainage or spacing length to the slope measure horizontally, that is L is equal to 30 meter, the liner slope, that is beta is equal to 18.263 degree, permeability of the vegetable supporting, that K base is 0.0001 centimeter per second, overall factor of safety to the drainage Fs is equal to 3, and these are the reduction factor for the intrusion, reduction factor for the creep, reduction for the clogging, and reduction for the biological clogging. So, you are doing 1.2, 1.4, 1.2 and 1.5, and then you calculate and find that the required ultimate transmittivity of the geomembrane geosynthetic clay liner lining system is theta is equal to 20.27 centimeter per second. So, next lateral drainage system in the Giroud method. So, Giroud method also this is the lateral drainage system for the Giroud method. This is the equation has been used into this program, and this is the drainage pipe, that spacing length of the measurement horizontally L is equal to 30 meter, the liner slope angle beta is equal to 1.345, that is degree, and this is the impregnated rate, that QI centimeter per second is 0.00001, and the thickness of the liquid collective layer on the geocomposite GCL, that is 0.75, that is centimeter, and the overall factor of safety for drainage, that is Fs is equal to 3, and these are the reduction factor for the intrusion, creep, and the chemical clogging and biological clogging. So, you have taken 1.2, 1.4, 1.5 and 1.3, and then you calculate and find the required ultimate transmittivity of the geomembrane or the GCL line system, that is theta 14.73 centimeter per second. So, then design of the landfill for access ramp, that is access ramp 1, and when there is a access ramp like this, when the vehicle should move in which direction, from top to the bottom or bottom to the top. So, these are the equation has been used for this, and this is the vehicle weight, that is W, V is equal to that is 55 metric tons, and unit weight of the base layer gamma 2100 kilonewton per meter, Q, and minimum interface friction angle delta is equal to 12 degree, and the ramp geometry, that is width is equal to W is equal to 6 meter, thickness T is equal to that is 0.61 meter, and the length is equal to L 50 meter, and slope angle degree is beta is 8. So, if you can calculate this, then you can determine factor of safety in the static condition 1.51, factor of safety in dynamic condition 1.19. So, this is the design for the landfill access 1. Design for the landfill access 2. So, this is that it may ramp like this. So, these are the equation has been used, and then the input data vehicle property, that weight W is 50 metric tons, the number of axis is 2, and that is wheel per axis M is equal to the 4, and this is the tar pressure, that is sigma tar pressure is equal to 480 kilonewton per meter square. Then ram geometry, that is thickness, is equal to 0.6 meter, and geomembrane and GCL property sigma of geomembrane is 350 kilonewton per meter cube. So if you can calculate, you can calculate the what will be the factor of safety. This is 11.39, so it is the safe. So leakage rate through the composite liner. So leakage rate through the composite liner. So this is, there is a leakage, this is the geomembrane material, and then how you can see that how leakage is occur. So leakage rate through the geocomposite liner. So we have used this equation, and then we put that consider of the geomembrane area, that is A is equal to 4000 meter square. Hydraulic head on the top of the geomembrane H is equal to 0.3 meter. Thickness of the low permeability soil, that is TS, is 2 meter, and the permeability of the lower permeability soil Ks is equal to this value meter per second. Number of the defect, let us say, is equal to 1, and the contact quality factor, that is CQO, is 0.21, and properties of the circular defect, that is diameter of the defect D is equal to 0.002 meter, and properties of the square defect, that means side length defect, that is B is equal to 0.002 meter. So if you can calculate, so you can have the output, what is the leakage rate due to the circular. So you can obtain this value, this gallon per or this liter per day, 1.934 liter per day, and leakage due to the square defect, then 3.14094 liter per hectare per day. So next is drainage designing with the SS ram. So drainage design with the SS ram. So this is the drainage design for the SS ram. This is the equation has been used, and this is the input data. Surface water parameter, area of the water A is 400 meter square, rainfall intensity is 1.0 centimeter per year, and the transmittivity theta is 0.001 meter cube per s meter. This is ram property, that is width is equal to 6.0 meter, thickness is equal to 0.6 meter, slope is equal to 8, and the permeability K is equal to 0.001 meter per second. This is the output data, Fs is equal to 1.21. So it is safe. Now this geometric puncture protection. So geometric puncture protection. So if there is a puncture, geometric puncture protection. So this is equation has been used, and this is the input data. Geotextile mass per unit area is 430 gram per meter square. Depth of the material on the top of the geomembrane D is equal to 50 meter, and the unit weight of the mass on the top of the geomembrane gamma is 12 kilonewton per meter cube, and portion length, this H, is equal to 0.025 meter. And this is the modified reduction factor. This is MF is 0.5, MF PD, that is modification factor for the packing density, is 0.83, modification factor for arching solidified, MAA is 0.25. This is modification factor for long term creep, RFCR is 1.5, and this is the reduction factor for chemical and biological clogging, that is 1.3. So if you can calculate, you can have the output data factor of safety 2.998. So comment that we can also find out the what will be the required geotextile mass per unit area desired for the factor of safety. Required factor of safety Fs is equal to 1.3, and you can also calculate, you can determine that mass per unit area is 455.988 gram per meter square. So you can determine what will be the mass per unit area. Now then design of the lateral drainage layer of the two composite slope. So, this is the two composite slope. This equation has been used, and this input data is given impregnated that rate, that is this value, and L is equal to 26, this L down is 40, K is equal to 0.2, K down is 0.1, beta is equal to 4.0 and beta down is equal to 2.4. This is all the reduction factor, and you calculate, and you can have the what is at upstream, what is at the downstream. So, you can obtain this value. Ultimately, you will have that what will be the required transmittivity value and what will be the ultimate transmittivity value in the upstream. Also in the downstream, you can calculate what will be the maximum liquid depth, what will be the required transmittivity, and what will be the ultimate transmittivity. So, this also you can calculate from this software. Also, the design of drainage layer for the two different slope. This I mentioned, transmittivity equivalency of geosynthetic drain and the soil liner. So, this is the transmittivity equivalency of geosynthetic drainage soil. The slope angle beta is 4.75, the slope length this L 20.2, and the soil drain thickness. So, this is the equation has been used, and then you calculate the equivalency factor is 1.1.2. And then the landfill gas pressure relief layer. It is also required to you can provide with the gas pressure relief layer. So, here is the liquid landfill gas pressure relief layer. So, this is the equation has been used, and then this is the estimated LFG mass flux. This is landfill gas generation, that is 0.00024, that is this is the unit meter cube per kg per year. Average waste, that is H waste is equal to 50 meter, unit weight of the waste gamma waste is equal to 8000, that is kilonewton per meter cube, thickness of the relief weight T relief 0.008, and the LFG relief layer transmittivity value, that is the maximum LFG pressure U is upper 2 kilopascal, unit weight of Lg, that is gamma Lg is 0.012 kilonewton per meter cube, spacing between the steep drain, that is L is equal to 20 meter, and these are all the reduction factor for intrusion, for the creep, for the chemical clogging and the reduction. This is biological clogging and overall factor of safety, that is 1.2, 1.4, 1.2, 1.5 and the 2.0. So, the landfill output gas pressure relief, you can have that mass flux by Ug is 0.8068, this is the theta required LFG 0.2582, and this is the epsilon ultimate LFG is 1.5615, and epsilon ultimate is equal to 15.640, and this is the total serviceability factor, TSF is 6.068, and the Reynolds number is equal to 7.9. Geocomposite gas pressure relief layer. So, this is the problem statement that software evaluate the transmittivity of geocomposite layer required to release the pressure build up due to gas. Now, here that this is the geocomposite gas pressure relief layer under the surface impoundment, and this is the equation has been used in this program. Now, input data gas relief layer underneath pond, that is pond gas flux, that is pi pond is equal to this meter cube per second per meter square, and pond length L is 200 meter, allowable mass gas pressure U maximum is equal to 3, and unit weight of gas gamma G 0.12 kilonewton per meter. And this is the reduction factor for the intrusion reduction factor, then creep reduction factor, chemical clogging reduction factor, this is biological clogging reduction factor, and this is overall factor of safety. So, this is 1.2, 1.4, 1.2, 1.5 and then 2. So, you can calculate and you can have the output, that is pond gas flow rate, that will be that QPG is 0.120 10 to the power minus 5 meter cube per second per meter, and required PG layer transmittivity, that is theta required PG 0.144 10 to the power minus 5 meter cube per second per meter. Then ultimate PG layer transmittivity meter cube per second meter into 10 to the power minus 5 is 0.8709, and the hydraulic transmittivity into 10 to the power minus 5 this meter square per second, that is theta is equal to 8.7091, and total serviceability factor TSF is equal to 6.048. So, you can go with all this detail about the program and can design the thoroughly. So, you require the proper kind of the design of the landfill using this software. With this, I finish my lecture today. Let us hear from you any question. Thanks for listening.